Hi there. Today we're going to talk about optimization, which is really what most people use calculus for. So um, let's make sure we're comfortable with some of the definitions that we'll be using, and let's motivate the definitions in higher dimensions with our definitions that we're already comfortable with. So um, we have a function, and we can talk about a local maximum, and a local maximum at x equals a means that if you are near a, then all the function values are less than or equal to the function value at a. Similarly, a local minimum at a means that when you're near a, all function values are bigger than or equal to f of a. Right? What about a global extreme? Right? So if we were talking about a global extreme, then it wouldn't be that all points near a satisfy f of x is greater than or equal to a, is greater than or equal to a, but instead that all points are bigger than or equal to f of a. So local extreme corresponds to being in a little neighborhood. These are also called relative extrema. And global extrema, or so global or absolute extreme, are when you have functions that, when you're looking at the whole domain of your set. So when we're talking about functions of multiple variables, now we have a function, a picture that looks like this. We're dealing with a point AB, and we have some function value of AB there. All right, and so what does it mean to be a local maximum? It means that if you're nearby, if you're in some little disk around AB, then all the function values of your function end up being less than f of AB, less than or equal to. Similarly, a local minimum is going to be when you're at your point AB and all function values are bigger than or equal to f of AB in some circle, some disk around it. And then global absolute, that's talking about over the whole set. So if in the whole domain the function value is as small as possible, that is a global minimum. And if you're in over the whole domain and the function is as big as possible, that's a global maximum. So one of the things we know back from single variable calculus and that we used as a tool to find local maxes and local mins was that if you have a local max or a local min, what did we do? We took a derivative and we set it equal to 0. And we said if there's a max or a min, then we have that f primed of a is equal to 0 or f primed of a does not exist. So this is kind of the backwards direction. This isn't totally helpful because the important thing is that it's not always the case that this is true, that the other way around. You always took the derivative, saw if it was where it was equal to 0 or if it didn't exist, and that's called a critical point. And we use that as a test. We use that to say, hey, wait, this might be a place where you got a local max or a local min, but it didn't have to happen. Remember when you had like y equals x cubed. This point, the derivative of this point, was 0, but it's not a local max, it's not a local min, so you have to be careful here. Same thing is true when you're doing functions of multiple variables. So just like before, we needed that the derivative was equal to 0. So in this case, we need that both the x derivative and the y derivative are both either equal to 0 or not exist. So we need to check, we need to take the partial derivative with respect to x, partial derivative with respect to y, check to find where those are 0 or not exist. Those are called our critical points, and those are going to be our testing points. Those are going to be the ones that we're going to try and see if they're the max or the mins. All right, but just like before, if both of them are equal to 0 or they don't exist, that doesn't necessarily mean that you have found a local extreme. All right, and so I think it's really important here as you're reading through the book or as you're trying to write things for yourself, there's a difference between a maximum and a maximum value. So a maximum or minimum is the x or the xy pair in the domain that where the function has an extreme. In the domain where the function has an extreme. Whereas, on the other hand, when we're talking about maximum value or minimum value, that's referring to the function value. That's referring to the f of x or the f of xy. So this is the y is equal to f of x or z is equal to f of xy. That's the place where the function, that's the value. That's the high value, either locally or globally. So this is the point in the range that is the value of the maximum function value or the minimum function value. So that's what's happening in this definition. So not all is lost in terms of, we said we'd like to figure out when a function has a partial derivative, has a max, has a local max, has a local min. And the way we can figure this out is that we have a test. We have a way that we can figure out whether a critical point is a local extremum or not. So here's what we have to do. So you need two things to be true. If the second partial derivatives are continuous around AB, so if you can take two derivatives of your function, both x partial derivatives, both y partial derivatives, and then x and y partial derivatives, and if you have the partial derivative with respect to x and the partial derivative with respect to y are both 0, then you can use this test. So these things need to be true before we can use this test. So if you're in this case, we're going to define d of AB. This is going to be the discriminant of AB. And the way we're going to get it is we're going to do the partial derivative, the second partial derivative with respect to x, times the second partial derivative with respect to y, minus the square of the mixed partial, f sub xy of AB squared. Now there's a really nice matrix form of this. It's the determinant of this matrix. So you can either, if you know, either of these two ways are exactly, it's the same formula. And so we look at this discriminant and we decide if the discriminant is bigger than 0. So this thing, if this number that we get here is bigger than 0, and the second partial derivative with respect to x is positive, well, the second partial with respect to x is positive, that's telling us, oh, this is the other way around. This should make you think about your first, your single variable calculus when you were saying, okay, well, if it's concave up, then we have a local minimum. Same thing here. If your partial derivatives are positive, you have a local minimum. On the other hand, if this discriminant is positive and f sub xx, so the second partial derivative, is less than 0, then we have a local minimum. So a local maximum, because now this is saying the slope is going down in the x direction. So when you have this discriminant is greater than 0, you have a local max or a local min if this is not equal to 0. If the discriminant is less than 0, then you're actually in this case, which we saw with our hyper, what's the right way? The hyperbolic paraboloid. I always forget that name. The hyperbolic paraboloid that kind of looks like a Pringles chip. If you're in that case, this is called a saddle, and you have a saddle point. And so if the discriminant is less than 0, you have a saddle point. But if d is equal to 0, so if you get a 0 discriminant, then the test is inconclusive. And so you'll have to figure out some other way, whether you have a critical point, whether you have a local extreme or not. All right, let's do an example. Find the local extrema and the saddle points of this function. All right, so how do we do this? We have to find the critical points. So we take the derivative, df dx is equal to what? It's 4x cubed minus 4y, and we have to have df dy is equal to 4y cubed minus 4x. So we need both this equation and this equation to either be equal to 0 or not exist. Now these are polynomials, so they always exist. So we only have to check to see when these derivatives are 0. All right, so what is this first thing saying? This is saying that y is equal to x cubed, and this is saying that x is equal to y cubed. So if we solve these two equations, what do we get? We get y is equal to x cubed, and x is equal to y cubed. Okay, so what are the solutions to that? Well, let's substitute this into here. What do we get? We get x is equal to x cubed cubed, which is saying that x to the 9th minus x is equal to 0. Wow, we've never really had to solve something like that before. We can factor out an x, and we get x to the 8th minus 1 is equal to 0. And so what do we get? We get x to the 8th is equal to x to the 4th plus 1 times x to the 4th minus 1. And x to the 4th minus 1 is x squared plus 1 times x squared minus 1. And x squared minus 1 is equal to x plus 1 times x minus 1. And so in order for this whole product to be 0, excuse me, I kind of got in the way here. For this whole product to be 0, we either have to have x is equal to 0, or x is equal to 1, or x is equal to negative 1. Those are the only options that give us 0 in this product. And plugging those back in here means we have to keep track of x equals 0, x equals 1, x equals negative 1. That gives us points 1, comma, positive 1, 1, 0, 0, and negative 1, negative 1. Those are our 3 critical points. Great. Now we have to figure out if the second derivatives exist and use the this discriminant to figure it out. All right, let's quickly go back to our other page, and get this information. Oh, doesn't want to do this for me, does it? Oh, here we go, good. So the discriminant, we have to calculate f sub xx. times f sub y minus f sub xy squared. So let's do that. So let's calculate f sub xx. So the derivative of this with respect to x is 12x squared. F sub xy is equal to negative 4. F sub yy is equal to, the derivative of this with respect to y is 12y squared, and f sub yx, because everything behaves nicely, that's the same thing as f sub xy, is also negative 4. So we calculate 12x squared times 12y squared, so this is d of ab, or d of xy, is equal to 12x squared y times 12y squared minus negative 4 times negative 4. So that's 144x squared y squared minus 16. And we plug in our 3 different critical points. So we have critical points at negative 1, 0, 0, and 1, 1. When we plug in negative 1, we get 144 times 1 minus 16, which is positive. Yay! And then we have 144 again minus 16. That's positive. Yay! And then we have plug in 0, 0. 144 times 0 times 0 is 0 minus 16. That's negative. Boo! I don't know. I think it's just great that we have some solutions. And then we have to check what is f sub xx here. Here f sub xx is equal to 12x squared, which is greater than 0. So, what does that mean? We know that negative 1, same thing here. F sub xx is greater than 0. So at these 2 points, we have a local min. Let me use a different color. Min. No, black is better. Min. These are local mins because we've got this kind of concave upwards type of thing going on here. Whereas this is a saddle point. Okay, so this is a little bit weird. If you think about the types of functions that we've dealt with in the past, normally you have some maxes and you have some mins, and you don't have anything else kind of crazy. But here, what we're seeing is we have 2 mins and we have a saddle point. So let's go over to Mathematica and see what this function looks like so that we realize why we get this type of thing. So when we're plotting a function, we use plot3d, and we want to plot x to the 4th plus y to the 4th minus 4xy plus 1, where x goes from negative 2 to 2, y goes from negative 2 to 2, and let's do a plot, let's do a plot range from negative 2 to 2 as well, so the z value. Alright, so let me see, I think I need to use something like exclusion style none. Nope, that's not it. Clipping? I think it's clipping. Clipping style none. So here's our function, and when we're outside, so this is the max z value, so maybe we'll let it go up to 7. You can start to see that this function gets really big out here where x and y are positive, are getting bigger, which kind of makes sense because you get x squared, x to the 4th, y to the 4th, so 2 to the 4th is 16, 16 minus, I guess if x and y are opposite signs, this is going to be adding to it as well. But you can see we get at negative 1, and positive 1, we get local mins, and at 0, 0, we get a saddle point. And so if we want to know what the actual function values are, we could take this and we could say, I want x to be equal to 1, y to be equal to 1, and we see that the function value is equal to -1, which I guess we probably could have figured that out ourselves. All right, so let's stop here for now, and I'll see you shortly. We'll talk about some optimization.